Okay, so but you working through it now might be some of the confusion. So if we're going to go through and look at this particular question, what's the most reactive thing we see?
The hydride.
All right, so hopefully we zero in extra props.
Oh yes, because I always look at
You're doubling down now. It's awesome. All right, we're looking at hydride H minus, incredibly small. That's going to be our super reactive thing. So we need to find something that is positive to interact with it. So we can now go through and look at our other molecule, and what do we see within our other molecule?
We have a partial positive on the carbon connected to the oxygen.
Okay. So what we might pick up is a partial positive from that carbon, which means partial negative on that oxygen. Where are you getting that from?
The
I may regret that question, but go ahead, fire away.
oxygen is more electronegative than the
Okay. Which is fine. Saying the oxygen is more electronegative, I think we should push on that a little bit harder.
Because I wanted to say resonance, but that's not.
So the positive and negative we're probably just pushing at with partial positive and partial negative due to the electronegativity difference. But it's a step beyond just that because we do have that resonance option. And if we address that resonance option, that's actually going to call attention to the chemistry that we actually need to run this reaction. Can I get away with just drawing pH for the ring? Okay.
Yeah.
Thank you, Caden, for responding first. Okay. We could go through and we could draw those lone pairs. We'll draw the green one, making our oxygen negative and our carbon formally positive. Okay. So we now have a positive, right? So what could we do?
The hydride.
Hydride negative, come in and attack.
But I thought it couldn't do that.
Okay. I'm going to come back to you on that one. Okay, because we could then go through, right? We don't need to show that hydrogen anymore because we've gotten rid of the positive charge. We have the negative on the oxygen. If we're drawing this, we should stop. Okay. What happens in our next step?
The ethyl would come in, the positive ethyl.
We have a negative on our oxygen. We can recognize that iodine is electronegative. It would suck the electrons away from the carbon. Carbon giving us the positive. With negative to positive, we put the ethyl on there. And our next step, which I'm not going to draw the mechanism for, we'll see why in a second, or people that may have attempted to put this into SmartWork may know why. We enter it in SmartWork, nope, we're wrong. Okay, yes. Okay, we are wrong. Figuring out where we went wrong is a bit of a challenge. Okay, if we think about the step 2 part, there's only one negative and one positive. Okay, so I would argue step 2, you didn't have any choices. Like, that's it. Okay, so we could rewind back to step 1 and going on with that. We have 2 negatives, and they're fairly reactive negatives, and we have a positive. But that's still just one negative and positive. Is there something else we're missing? Now you want to chime in.
Oh, well, the hydride can't do a nucleophilic attack.
So this is now zeroing in on the specifics of the reagent. Sodium hydride is very, 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 very unstable. So unstable, we can't get the hydride stable enough on its own to come in and do a nucleophile attack. Okay? So that arrow we drew is great. It has a negative to positive, but that's not a feasible reaction for that particular reagent. Okay? Which means what? It means a couple things, but one, all of that work that I just drew out was wrong, so I told you to stop drawing. What else does it mean?
The hydride would have to act as a base.
Okay, so we can push that. That means the hydride is not acting as a nucleophile. It must be acting as a base. Okay, which is another way of saying there's another positive floating around and I'm just not acknowledging it. Okay, where's that other positive? If we acknowledge the hydride can't act as a nucleophile, it's acting as a base, we know that hydrogen must be acidic. Okay, so we could go through and we could look at a variety of hydrogens. We've got a hydrogen on that phenyl ring. I'm not drawing out that ring, so clearly that hydrogen's not the right choice. Okay, we've got a hydrogen out here, and we have a hydrogen in here. Okay. If we pulled the hydrogen off the phenyl ring, we form a negative carbon. And it's not resonance stabilized, perpendicular orbitals, all that fun stuff. We aren't like that. If we pull the purple hydrogen off, okay, we have, again, a negative carbon. That negative carbon is chilling out, no resonance to stabilize it. It's just a raw negative carbon. Okay? Not particularly great either. If we look at the blue one, it would be a negative carbon also, except what's right next to it?
A positive.
A positive. Could we combine the negative and the positive? Yeah, that would potentially stabilize that well enough so that it could come into existence. So it makes the most sense for our hydride with its lone pair to come in and attack our hydrogen. The electrons in that carbon-hydrogen bond can then go in to stabilize the forming, or the, depending on how you want to draw it or think about it, and this is as good as opportunity as any with this question, we'll come back to it in a second, to address proper mechanisms, because officially, I did not draw one. Right? And yeah, you can twist your head at me, we'll talk about it. It's semantics. In my opinion, it's semantics. So that neutralizes it. The other thing that we could evaluate is that that is a resonance stabilized structure, because we could oscillate, try and focus on using curved arrows as green, and we get these two structures that we're working with now. Okay. Which one of those two is the one that we would predict to continue our reaction forwards?
One with the negative charge and oxygen.
Okay, so we've got A and we've got B. We've got a vote for A. Why do you want to say a vote for A?
Because oxygen is both more electronegative and can just hold more electrons in general, therefore it can stabilize the charge.
Cool. And for those people at home that may not have heard that, oxygen is great at being able to stabilize a negative charge. More electronegative, it can hold its electrons. What's the very next thing we want to have happen? It needs to react. And if oxygen can hold the electrons better, it's not going to react. So A isn't our reactive structure. A is what I would reference as our best structure. We want the useful one.
Well, at the same time, is eliminating that charge and that oxygen still not more stable, if that makes any sense?
So your argument is, why don't I take that negative and eliminate the charge? What about the other resonance structure? I already eliminated the charge. So your argument of, well, if I react and I eliminate the charge, doesn't matter because I've eliminated the charge.
Well, yeah, but wouldn't that be the first product we get due to it being more stable as an intermediate compared to the final product, I suppose?
So then, and I full disclosure, not super happy about the difference between these two. And ultimately, this is something that goes back to chapter 7, and Carty does go through and look at the bond energetics between these two structures. If we go through and evaluate this, and these structures are going to show up again and again and again, so it is very important to recognize this being useful and this being best. Okay? What functional group do we have in our best? It's a strange one because it's charged. Okay? And since it's charged, that might be confusing. So let's temporarily remove the charge.
Oh, I mean, with it, do you mean like a carbonyl? Oh, no, alcohol.
And in your response of saying alcohol, no.
Oh.
You have an alkene connected to an alcohol. Those two interact with each other. That's an enol. What's the other one? A ketone. What we're looking at is effectively the keto-enol tautomerization. Okay? It isn't technically a tautomerization here because we aren't looking at the ketone and the enol. We're looking at the intermediates that are along that path. Okay? So what these are typically referred to this is referred to as an, actually collectively, now that I think about it, an enolate. Enolate, the 8 is supposed to reference the ion. If you think back to carbonate, sulfate, okay, all of those complex ions that you theoretically memorized back in Gen Chem and then immediately forgot, okay, we're all negatively charged oxygens when we saw that 8 ending. We're looking at a negative charge. Whoops, I dropped that oxygen's negative. Okay, sitting in that. So it's how those electrons resonate back and forth, and that's what's known as our enolate. Okay? So we could pull up the same statistics of the keto-enol tautomerization and say which one is more stable, the keto versus the enol. Okay? And yeah, you can come up with arguments. I would argue kind of both directions. Okay? The one that I use kind of best in my head is that if we looked at continuing these kind of reactions forwards, if I look at the best resonance structure going forward, that oxygen is sharing electrons with 2 atoms, which means its electrons are being drawn away from it. Whereas in the other structure, the oxygen isn't sharing electrons with 2 atoms, it's sharing them with 1, which means the keto form, the oxygen is holding its electrons a little bit tighter than it is in the enol form. That's my half-assed argument. Okay? Carty goes through and makes an argument of bond energies and quantifies all the bond energies. That's way too many numbers for me to deal with. But if you've got the textbook, you can open up, I think it's in chapter 7. Okay? And he goes through and talks about the energetics between the keto and the enol form. Okay? Ultimately, the biggest thing that we need to acknowledge is that when we're looking at anything that looks like that vein, the useful is your, and I forgot to put the charge back on our carbon. The useful is with the negative carbon. That's the one that propagates out. Okay. I will throw out there also as a potential caveat. Does that mean the oxygen is never negative and can now potentially react as a negative? No, it absolutely can, but you're looking at very limited scenarios for that situation to happen. Universal or most applications, it's looking at the carbon being the nucleophile. Okay? Kind of, sort of? Okay. So now what happens? We've got a negative atom again. Between the 2 resonance forms, we established the useful is the more useful one. There's my negative. I can go back to step 2. Step 2 shows me that I have that positive carbon. And we can get a little bit more detailed with our reaction now. There's our CH3. What am I trying to draw? H, Ri. Our nucleophile comes in. Why does it do it in one step? What type of reaction am I showing here?
Backside attack.
Backside attack is lovely. You're answering the mechanism. Okay, and even then, we don't have a mechanism that's called backside attack. That's our description of it. What's the reaction? You're getting into the mechanism again, which is fine.
Oh,
we can work with that.
Huh.
What's the mechanism?
Rearrangement?
It's substitution. Okay. What did our enolate act as? It's the nucleophile. It supplied electrons to our carbon structure, which kicked out the leaving group of the iodide. Okay. What kind of mechanism is this? As a hint, backside attack is the colloquial term that we would use as our interpretation of said mechanism. But what's the mechanism? It's SN2. So our reaction is substitution. I'm going to not write that all the way out. This is SN2. Why should we draw it as an SN2 and not show it as an SN1?
Because it's being stepwise would be more...
Backing away from that one. What do you got? We're not showing the carbocation. Well, why did we not show the carbocation? Just because I didn't draw it doesn't mean it didn't happen. I'm asking why should it happen as a simultaneous, not as a stepwise? Okay, so we could look at the substrate. The substrate, okay, if we colored it in here, looking at that for our carbon structure, would be a primary leaving group system that would generate a primary carbocation. Our primary carbocation is stable. No, so we shouldn't show the carbocation. Why else should it be SN2? Not going to appreciate it, Caden, but I'm going to call you out for it.
Okay.
Nope, wrong structure.
That is good leaving group.
Wrong structure. There are 4 things to consider when looking at SN1 versus SN2. Okay? Leaving group, pretty useless, okay? Because both SN1 and SN2 involve leaving group. Okay? You just got an O, so maybe you have the answer, but hold it. Okay? We could talk about the substrate. We just did. We could look at the solvent we've ignored, so it's not the solvent, it's the last remaining thing, which is the nucleophile, which is, Caden, why you should have gotten it, because you were the one that called attention to that being the nucleophile or enolate. Okay? And if we look at that, and that's okay, our nucleophile, is it strong or weak? Strong. It's strong, and if it's strong, that favors SN2. So we have 2 pieces of evidence that would suggest this mechanism should happen all at once, not stepwise. Make sense? Okay. This sets us up with our final answer. If you put that in there as an O, not as a 6. Okay, come on, I thought that was funny. Okay, you should be good and get your answer correct as far as that one goes. Okay, at the very beginning of this, I did kind of push on this and say, we need to double back and talk about mechanisms because what I've technically drawn is not a good mechanism. Okay? Different instructors care at different levels behind it. Okay? It's a semantic argument more than anything else, at least in my opinion. But I don't care, so clearly I'm going to blow it off as a minor point. If we look at where our mechanism actually started, where did it start?
At the hydride?
Yeah, it started at the hydride. That's where our mechanism actually initiated. Okay? If we look at what the hydride is reacting with, what is it reacting with? What is this structure? Is that the best Lewis structure? No, why not? You're all saying, like, well, I don't know why there's best or not.
Because it's showing it's charged.
It's charged. That structure is not the best Lewis structure. It's the charged Lewis structure. It's the useful resonance form that allows me to predict where the chemistry is located so that I can navigate my system. Okay, so it allows me to understand the chemistry. Okay. However, this structure is not what I should be reacting. What I should be reacting is the most, or is the best one, which means my hydride should actually be reacting with the top structure. So if we were to go through and look at the mechanism more appropriately, what we would go through and do is show that hydride, or that hydrogen. Our electrons come in. We'll use red arrows this time because we're highlighting a different system. The electrons going up. We would have our phenyl. We got our oxygen. There's our double bond. Oxygen being negative. Okay, we could have the electrons come back down. Those electrons swing out and attack our CH2. CH3 with the iodine and the electrons breaking out, giving us our final product. Okay, so showing a better mechanism across the top. Okay. The issue that I have behind that is that there's a lot of implied chemistry behind it that isn't obvious if you aren't an experienced viewer on chemistry. Okay? All of those resonance structures we drew to help us understand how and why and where the chemistry is happening aren't addressed. So if we only look at the best form, you as students learning the content miss all of the underpinnings that allow that mechanism to be best.
Isn't it typically addressed with the partial charges shown in the beginning structure?
Partial, well, did I show a partial charge on the hydrogen? And even then, our partial charges things that exist. They're markers for us to identify where the chemistry is. And even when we did that, we marked them, but not in a way that actually showed the mechanism.
That's true.
So even the partial charges aren't things that are on standard mechanisms. Think to all the mechanisms you had to draw in SmartWork. In any of those, did you have to show partial charges? No. Okay. We are adding partial charges to the drawings that we generate to help us get a feel for where the chemistry is located so that we can predict what the mechanism would look like. Okay? This giant mess that we're showing down here is our thought process written out. That red stuff along the top is what you would see in a textbook. Okay? It's what you would see as an answer. Okay? Work is almost always messier than the cleaned up version. But that work part is the thing that you need to struggle through and work with, because the top part is ultimately going to be memorization for you at this point. It's not really an understanding yet because you don't have those underpinnings to support it. Kind of, sort of? We will encounter multiple issues like this within SmartWork because there's a couple cases that have already popped up for a few students when dealing with drawing out mechanisms, because what you're drawing out is mechanisms that allow you to see the chemistry, but that's not proper language for how you draw a mechanism, and SmartWork is more focused on what is the proper mechanism behind it. And so I know for sure you encountered that issue, and it will pop up at least once more this semester when you're trying to draw out mechanisms. Okay? But I think it'll actually show up for everybody probably 2 or 3 times. Okay? So just want you to be aware of that. You could easily be doing something correct as far as your mechanism process, but then if you get drawing out SmartWork and you're like, well, but I'm out of boxes, it's because what you did was showed your work when they didn't ask for work. So you got to be a little bit careful with that process. It's one of the reasons why I want you to email me if you're struggling with a question. Because you could very well know the content, but be missing the formal language behind it. Sound good? Ish? Okay. Next question? You wanted something on that?
Oh, no, that's for a long question.
Okay, yeah, what's up?
The carbon evolutions question 10.
Did you just say it's the one that you just struggled with, that we just talked through?
Yeah.
Okay. It's not a grouped question, so we'll just drop into Anthony's. So, there's a couple things going on within this one, okay, and we'll talk through why, and you may very well repeat your, it's not excrement, explicative. Okay. I knew it was an X word. Okay, after we kind of address the details behind this. So, first thing I would kind of point out here is just what things changed. Because here you're trying to find reagents. If you can identify what changed, hopefully you can figure out what the reagents might be. So what do we notice changing?
It's an addition reaction.
That's not answering my question, but okay, yes, it is an addition reaction.
How does that not directly answer your question?
I said what changed.
Yeah, and that tells you everything you need to know.
Yeah, not even close. What changed?
Pi bond's gone and there's
Okay.
2 new bonds.
So loss of a pi bond, okay, and we could say the gain of 2 sigma. Okay, what 2 sigma did you gain?
Hydrogen and butane.
Okay, that's good. I honestly don't know how many it is either.
I think it's 4.
Okay. To figure out exactly how many, what we could try and go back and do is backtrack out. This is where color coding can come in handy, right? Okay, which would then mean our new bond here, that piece we've got is 1, 2, 3, 4. Good job with the butane. Okay? So somehow or another, we need to pick a reagent that adds 4 carbons. So what we might go through and do is look at the list and be which of these reagents add 4 carbons. Okay? And what I believe the list of reagents will show you is that all your choices add 4 carbons. Or have 4 carbons, I should say. Not add 4 carbons. They all have 4 carbons. Okay? But we have to be a little bit more careful because we have to know the exact charge on those individual atoms. Okay? And this carbon-carbon bond forming is an interesting one. Okay? Why would that be an interesting bond to form? What charge must the carbons be?
Positive and a negative.
One needs to be positive. That's not a big deal. Carbons can be positive all the time. We see it all happen. The other one needs to be negative. There's the issue. Okay? So we can now go through our answer choices, because I think there's 4, and you could correct me if I'm wrong. Okay? And you'll find that one of those 4, there's 5. Okay? Okay? At least one of those 5, actually I'm going to think through this. I'm going to guess. One of those 5 shows a positive carbon, and one of those 5 shows a neutral, all 4 neutral carbons. All right? And then 3 show negative carbons. Yeah, look at that. Okay? So the neutral is wrong. Okay? Because it has to somehow be positive or negative. Okay? Well, which one do you want to assume for our answer choice? So our answer choice is now looking at the butane, okay? And in particular, that carbon. What do we want to make that carbon's charge?
Positive.
Okay? If we make it positive, what must the other carbon be? It has to be negative. Okay? That's fine. So let's work with that. Okay? And if that's true, only one answer works, right? Because we said there were 3 with negative butanes. Okay? Which should already set off a little alarm bell in the back of your head, like, it's probably not positive. Okay? But let's work through it. Okay? We don't know necessarily about the positive bromine structure, except that it's there. What we need to figure out is, can we make the negative carbon on our parent structure a valid system? Okay? So now we can go back to our parent structure and say, what do we see as reactive within that parent structure? And you now processed out the resonance. Okay? So slow it down, keep your mouth shut for the rest of this. What do we see? And I'm not saying that to be mean.
No.
Okay? What do we see is the reactivity now within that molecule? Okay? For reference, just in case it wasn't clear, there's our box. I want to know what reactivity we see for that particular molecule. You can name bond types, you can name actual like nucleophile, electrophile, acid base, all that. What's the chemistry you see within that? What's the primary thing that drives the reactivity of that molecule? The pi bond, awesome. Except there's 2 pi bonds. Okay, which pi bond is the primary driver for the chemistry on this? Why should the carbonyl oxygen one be the driver for this? The polar covalent bond is going to be the one that drives our chemistry. Okay? It doesn't mean that that's where all the chemistry is located. It just means that's the driver. That's what's going to dictate everything else. Okay? So let's take a look at that pi bond. What would we expect that pi bond to do? I accept resonance, but let's be more precise.
We actually need to pull the electrons.
The oxygen should pull the electrons away from the carbon because oxygen is more electronegative. So if we're looking at a potential resonance, we could draw this system. With the negative charge, I'm still trying to get used to color coding things. Okay. And then the positive charge on our carbon, right? Of those 2 charges, which one are we more concerned about?
Positive carbon.
Why is the positive carbon more concerning?
It's more unstable than the negative oxygen.
Why is it more unstable?
Damn it. I know it is.
No. The smartest underwater animal.
Squid? No. Octopus?
The what?
Octopus? Oh, octet.
Okay. The carbon is missing its octet. That's one of the biggest drivers behind stability in Lewis structure. So one of the reasons why we don't show resonance when we go through and do mechanisms, because you're drawing a structure that's missing its octet. Okay? So if carbon's our primary focus, that's now what's going to drive the rest of our now chemistry. Okay? If we push on this further, that carbon is positive. I wanted the other carbon to be reactive. Okay? So what I want to see is how that polar pi bond affects the chemistry getting out to that green dot. Kind of make sense? Okay? Well, if the positive carbon is now my driver, how could that positive carbon drive the chemistry all the way out to our green dot?
The electrons from the other pi bond.
Say again?
Was that other pi bond resonating?
Can you do more resonance? Yeah. And what does that do to that terminal carbon? It makes it positive. So if we now go through and look at, and we weren't trying to match what we wanted here, we just wanted to see what this structure would do. And when we track its chemistry, we find the polar covalent bond first. We address the polar pi bond. Oh, it's a pi bond. We can do resonance. We look at that. Oh, we're missing an octet. How could we stabilize that octet? We look at another pi bond. We could shift that across. And that now gets us chemistry at the exact position that we were trying to find chemistry for. Okay? With that tool, we can now backtrack to the work that we said. We wanted that carbon to be negative. It's positive. It's not negative. What does that mean about our assumption of the butane structure being the positive?
It's wrong.
It's wrong, which means don't select that answer. Okay? So we've now gotten rid of a whole bunch, or a whole bunch, 2 out of the 5 options. Okay? That's lovely, and I love all that work, and it's phenomenal, but what we're about to cross into is now moving into memorization. Okay? Because the remaining 3 reagents, so if we fix our charges now, negative, positive, okay? We've got our green positive. Now we're talking about that butane being negative, okay? And if we go through and look at it, we've got, is it lithium bonded to carbon? I know that's what I did in the tutoring center. I don't know if it was actually true. Yeah? And then it was magnesium bonded to carbon, and then it's copper bonded to carbon. Okay? And if we look at those 3 options, all of those are ionic bonds. Lithium, magnesium, and copper are all metals. Okay? And since they are all metals, the carbon is going to become negative in all 3 of those scenarios. So what might we reflex into?
Choosing all of them.
Choosing all of them. Okay? And of course, SmartWorks going to kick back that it's wrong, because it is wrong. Okay? And that's going to now push us to the next potential issue within this. Let's go back to our substrate. We said we wanted to figure out where the chemistry was, okay? And in particular, at that terminal carbon. We found that. But to find that, what else did I find?
That there's chemistry elsewhere?
There's chemistry elsewhere. In fact, when I look at that starting substrate, there are 2 positives. What does that mean? There are 2 possible products. I could get a product continuing on from here or continuing on from there. And when I do that, what am I ultimately referencing? Not you, Abby.
Yeah.
And that might be hard, so let's backtrack even further up the line, okay, further in backwards in class. Remember we looked at this reaction, right? And we reacted this with HBr. And we added the H plus first, and we get this. And then what do we say that could do? Resonance. And when we looked at that resonance option, what happened? Of course, it's now off the end of the thing. We had 2 reactive sites. If one of these reacted, we ended with a okay, we'll draw it all the way out. We ended here. If the other one reacted, we ended here.
Yeah, but did you want us to call that something? I don't know what to do with that.
is there anything that we could potentially call these? What's the relationship between those two products? Wrong letter.
What's it called? Is it the...
What's the difference between these two products?
The regiochemistry?
We could push it. Regiochemistry. What's that?
Kinetic versus
Okay, too late. What's the difference between these two products? What's the primary driver of the chemistry here?
Where the pi bond is?
The pi bond. Is there a difference in energy between those two pi bonds?
Yes.
Yeah, one is more substituted than the other, which makes that one more stable. And because it's more stable, we might call that the
Thermodynamic.
our thermodynamic product, and the other one would be our kinetic product. The kinetic product happens first because the intermediate was more stable, secondary versus primary. So the kinetic product had a lower transition state, lower activation barrier, so it formed first. If we had enough heat, we could reverse that reaction, and the thermodynamic would then be irreversible once it went through and formed. We have our intermediates being shown here, where we have a secondary carbocation with an oxygen right next door versus a primary carbocation. Which one's more stable? You could end up with a kinetic versus a thermodynamic. Okay? In the case where we looked at it in the past, we just said it was temperature. Temperature could mess with it. Okay? One of the things that we'd drawn up on the board, so it was, I don't think it was in any of the lectures, so can I erase my kinetic thermodynamic thing over here? Okay. One of the conversations that we had is that what's going to happen eventually, ta-da, okay, is we're going to achieve a different system. And if we were going to look at, say, a kinetic system, we might get an energy diagram that looks like this and a thermodynamic that looks like this. Right? Activation energies, all those things. And if we look, the relative distance between our reactants and our products is pretty close. Okay? That was the conversation we had with the one I erased. But remember, I also said in class, drew up on the board, that there's other ways we could run that reaction. We could have also run the reaction like this. Now the delta G changes up. It's still kinetic and thermodynamic. But if I now look at the reversibility of the kinetic product, that's really flipping hard. Okay? And that's where this unit, okay, and technically next unit really comes into play. And when we talk about hydrogens and carbons as nucleophiles, they're negative. They're insanely unstable. So if we're looking at putting H- and C-, their relative energies are through the roof as far as reactants. And we run the reaction, what happens? We usually end up with a negative oxygen as an intermediate. Relatively much more stable. Okay? Can I further make a carbon or hydrogen more or less negative?
Yeah.
Yeah, how? How could I make that carbon more or less negative?
By connecting either less or more electronegative things to it.
Awesome. If I put a carbon and I bond it to a hydrogen, that carbon does have some electron density, but that's a nonpolar covalent bond. That's a relatively tiny negative. So if we were looking at this as far as the energetics, that's probably something way the flip down here. Very, very tiny negative. Okay? But if I go to something slightly less electronegative than hydrogen, what's less electronegative than hydrogen?
Metal.
All of my metals, now I shoot through the roof and I'm now up at the top. Okay? Well, what's the difference between lithium, magnesium, and copper when it comes to our electronegativities?
They all have the same. Or is that not true?
Were you told to say memorize electronegativity trends? Because they're kind of important?
Vaguely.
Oh, yeah. Lithium's at the extreme upper left. Okay? Not the least electronegative, because francium is technically the least. Okay? But lithium is very low in electronegativity, which means the carbon being generated, or the negative charge being generated on that carbon is freaking huge. Copper, being significantly closer to our fluorine, is more electronegative, which means the carbon is now
A little bit
less negative. And the magnesium hovering somewhere in the middle is now hovering somewhere in the middle. What is that changing? That's changing the balance of reactants versus products, which, sorry, people at home, I'm not doing that, redrawing it like 6 times. Okay? But that's looking at our energy diagram and changing those. Eventually, we hit a point that what happens? We switch from favoring kinetic versus thermodynamic. There's always a tipping point. Okay? The tipping point is challenging. Okay? Tipping points you should memorize. Okay? When we look at the lithium carbon and the magnesium carbon, both of those are very reactive carbons. Because they are very reactive carbons, they react as fast as humanly possible to neutralize the negative charge. As fast as humanly possible. So what do they react with?
The oxygen.
I understand what you're saying, but the carbonyl carbon generating our kinetic product. This carbon copper isn't quite as negative. So how do I know what it reacts with? There's only 2 options. I've memorized the answer, or I go into the lab and test it. We can't go into the lab and test it really easily, so unfortunately you have to memorize that difference. Okay? And what happens is that carbon negative is small enough that it can chill for a little bit and it can decide to attack the positive that generates the most stable product, i.e. the thermodynamic. So what ends up happening is that the carbon-copper reagent is the only one that attacks that positive. All the others go the other spot, okay, or don't react, okay, because their negative is strong enough that it goes, nope, I got to kill this as fast as possible. Okay? The alkyl lithium, so stupidly reactive. Okay? We don't associate a name with that because we're like, no, it's just reactive, deal with it. Okay? Okay, so those are just reactive. Those are so reactive that typically we see them act as bases, not as nucleophiles. Because they're so they're immediately grabbing anything immediately, and that's going to be hydrogens on the surface. Okay? So they are very, very, very basic. Okay? So they're almost exclusively bases. If we think back to the Wittig reagent, the last reagent was
Lithium something.
butyl lithium, because we were trying to remove a hydrogen, basic. Okay? The next one, we've reduced some of that chemistry a little bit. We slowed it down so it didn't do the obvious chemistry. And since it didn't do the obvious chemistry, what did we do? We named it after the person that discovered it. And that's where we get, yeah, I think I did that right, Grignard reagents. The copper one has slowed it down even more, and so much more that it's targeting a different product, which then means we also name it. It's a Gilman reagent. Okay?
Wouldn't the Grignard,
It's okay.
wouldn't that act as an acid like first more than anything? Because isn't that the whole point of it? Is that not the base before acting as a nucleophile?
So could it act as a base? Yes, it has the potential to act as a base.
You said that it's most likely going to act.
It is, if there's something acidic enough to activate it.
Oh.
And so that becomes the hard line, which I'm surprised no one has actually challenged me on, to be honest. Okay? We do have some acidity, particularly in our alpha hydrogen out here. Why does it not attack that? It probably does, but it leads to a dead end that doesn't produce enough products to do anything useful. And so the primary result is, or the primary thing we see, is it attacking the carbonyl. Okay? When it's a hydrogen that's connected to an oxygen, that's now acidic enough that we shift and everything just kills the Grignard.
Oh, okay.
Right. So it's coming down to a slight kind of reversibility within that system. Okay? The Gilman now drops enough that we would favor our thermodynamic product. Okay? This, I don't dare to go back, but if we think back to our kinetic thermodynamic system, what was my starting material that I drew? The very first one. You guys remember reacted it with HBr?
Didn't have an OH in it?
Nope.
Oh, well, I tried.
Say that again? It had 2 pi bonds. We also have 2 pi bonds. That conjugated system is always going to mess with us because of this potential for resonance. Right? So when you're seeing conjugated systems, that's when you should slow down a little bit and be like, do I got to worry about kinetic versus thermodynamic? Okay? And you might, you may not. It just depends on that system.
I mean, except if it's in a brain.
Yeah. Okay? Kind of makes sense? Okay, with all of these reagents, we're adding really big negatives, which means the product of all of those reactions is going to be negative.
Oh.
Okay, can't cancel out the charge. So if I'm throwing in big negatives, the counter ions of my metals are not going to stabilize that. I'm going to generate a negative in my structure. If we go back and look, I forgot to draw the negative on that one. Okay, but we get our negative oxygen in each of these cases. Okay? So what ends up happening is that we have to quench that negative. We have to remove it somehow by adding a positive. What would be the easiest positive that we could add? Hydrogen. So if we now move to our reagent 2, okay, what are we adding? Hydrogen. We need a source of H+. So now it becomes which of those reagents provide me H+. Okay? The one that always trips me up, water. Because, yeah, it does, kind of, not really, sort of, yes, it does.
Oh, it does? Okay.
Yes. Okay. The rest, I think you should be able to figure out if you think about their structures. The water one is tricky, okay? But the others, you should be able to reason through and figure out what those results are. Okay? Kind of, sort of? Okay.
Is it, with the water, is it a weird thing where is it like the oxygens connect, kicks out hydrogen, and the oxygen fucks off? I can't remember. It's weird. I don't like it.
It's just an acid-base reaction, bro.
Fine, whatever.
Sorry.
That
Yeah.
would be it.
Yeah, guy walks into a bar and orders a glass of H2O. His friend orders a glass of H2O too and dies.
It's so terrible.
You started it. Okay? If we go through and evaluate these overall reactions, okay, if we come back to these, because you'll hear some more terminology pop up with these reagents. Okay, you can see the alkyl lithiums act as nucleophiles. So that does happen. It's a secondary case. I would argue it's more of an edge case for those. Okay? And when we talk about those nucleophiles, when they do the addition that you so astutely pointed out, we're adding 2 atoms. Okay? We're adding an H and a carbon. Okay? And where we add those atoms becomes a name that we could then associate with that reaction. So we would typically call those reactions 1,2, technically nucleophile or hydride, 1,2 nucleophile additions. So you might hear reference to 1,2 additions. That says addition, I just ran out of space. Okay. The Grignard. The Grignard is acting the same way. It's adding the hydrogen to our oxygen, okay, and the nucleophile to our carbocation of the resonance of our carbonyl. So that also gets this name of a 1,2 addition. What does the Gilman go through and do? Well, it adds the hydrogen and the carbon, but where does it add the hydrogen and carbon to?
A different position.
Right. What's the 1,2 in reference to? Okay, is it the carbon chain? When we talk about the Gilman, okay, I don't know if you were actually shaking your head no or not.
I kind of remember something with the pi bond, right?
Yeah. We're adding the hydrogen to the oxygen, so I can't tell me it's part of the carbon chain. And then I add it to the carbon. Well, if I could define one of those as position 1 and the other one as position 2, there's 1,2. Ta-da, 1,2 addition. What happens with the Gilman? I add hydrogen and I add carbon, but I add it to a different pi bond. Where's the new hydrogen in my product? Try it again. Where's the new carbon in my product?
The blue bond?
The blue bond, okay? So there's my purple,
Yes.
okay? Where's the new hydrogen added? And it might be baffling because you're now trying to take out numbers. Don't think about numbers. Where's the hydrogen supposed to end up? It won't be at that positive spot because that positive was quenched by our negative of this one.
Won't it go on that negative carbon? I wish I could say how the word for the alpha carbon on the right. That one.
Cool.
Yeah.
Yep, there's where our hydrogen goes. Okay? Because when we look, that's where the pi bond was, and we added H and carbon across that. So let's define position 1 where the hydrogen went. Where did the carbon go then?
Position 3,
And
2,
2. So we would call it a
1, 2 addition.
1, 2. But aren't they adding them differently? Why would we call them the same name? Took me frickin' forever to figure this out. I could never understand why. Because when we talk about the Gilman, it's not a 1-2 addition. Guess what it's called?
1-4.
A 1-4 addition. What the hell? Why is it called a 1-4 addition? Okay. To figure out why we call it a 1-4 and not a 1-2, we actually have to propagate our reaction a little bit further along. So what I'm going to do is delete these things. Okay? Because in the case of this, we didn't actually show how to get the product, right? We just said that it should attack there and we'd be happy. Okay? So our butane carbon structure, our carbon negative, comes in, goes boop, forms that bond. What do we get? And then we get our, make sure I got it right, our 4 plus carbons out there. And we get our negative charge on our oxygen. Yeah? So far, so good? So now what do we do?
We'll show the other. I don't know. You don't show resonance.
We add the acid. And where does the acid go?
To the partially negative carbon.
It's not partially negative. It's formally negative. And ta-da, there's our product. Is that what's shown above? No. We'll get back to that. Where did I add the hydrogen?
To the partially negative carbon.
Where did I add the hydrogen?
Oh, on the oxygen.
To the oxygen. We defined it where we put the hydrogen as position 1. Where did the carbon go? 2, 3, 4. Ta-da, there's the carbon structure. I add the carbon at position 4 and the hydrogen at position 1. That's why we call it a 1-4 addition. But that's not the flippin' product. Why is it not the flippin' product?
Keto-enol.
It's a keto-enol. We form the enol form, which tautomerizes back to the ketone form to be our final product, which then swaps the hydrogen around and hides the fact that we did a 1-4 addition.
That's fucking bullshit.
Yeah, it is. But that's where that name is coming from. I want you to be aware of that in case you see that, in case you stumble across the exact same thing I did. It was like, I'm still adding it to 2 carbons right next to each other. I don't get it. Okay? It's because of your mechanism. You end up forming the enol. The enol tautomerizes and hides the 1-4 addition. Okay? But it is still technically a 1-4 addition. Those words will pop up. How much do you actually need to know those words? It comes down to how questions get asked. Like I said, I will try to always specify the words and then provide the chemical structures of those reagents to kind of minimize some of that word soup need to memorize. Okay? Which doesn't make it easier for the record. Doesn't really make it harder either, I think. But we good? So your question? You happy? Enough? Okay.
Oh, wait, but it also asks about what other reagents you could. Oh, wait, yeah, one of
Yeah.
them isn't even, yeah.
That was our hydrogen.
Yeah,
Yeah, we just needed a positive hydrogen. So you had to look through the reagents to find whichever ones supply positive hydrogens. Water's the tricky one, in my opinion. Okay, you can absolutely go through and do it and be like, no, Mike, you're wrong. All of them are tricky. That's fine. We can talk about those. Okay. But yeah, water to me is the tricky one. The rest are okay. Other questions?
11 on the same artwork.
Okay. We'll go to 11. I just happened to flip through my head one thing I wanted to address. When we talked about the reactivity of these things, we said we started with super strong nucleophiles. And if we noticed what happened, oh no, they're still here. Well, sort of here. We started with the lithium, super strong negative. Then we did Grignard, which was a little bit less strong negative, but still did the same chemistry. And then we did Gilman, which was less strong. And then what happens when we get less strong? We move to oxygen, which is in the next chapter. Okay? So this first chapter is primarily all of the strong nucleophiles, or what I would call stupid strong nucleophiles. Okay? And we're starting to transition into that now weaker nucleophiles, and that's why Gilman shows up kind of at the tail end. Okay. Just wanted to point that out. That was all that was. Work with me. I swear my finger isn't that fat. What?
Yeah, you see why I want help with it?
Does anybody else want help? Oh, I didn't hear any answers. Sorry, we'll do a different question.
Fair enough.
Okay.
You're not even excited to do this one.
No, but it is something that you need experience with. I kind of disagree philosophically with this kind of question, but I do know ACS has asked questions like that. In the past, I think they're starting to shift away from questions like this because the point is you should be able to interpret spectroscopy, not interpret a bunch of words on a flipping page. Okay, so they should just give you the image. Okay, but yeah, I think some of the older ones, the 90s exams, this is all how spectroscopy was presented. They didn't give you anything. You just 90s. You can't print pictures.
You couldn't print
technology.
pictures back in your
It's not quite that bad, but it's yeah. Getting the images into a document was not easy. So HNMR, there's a couple things we do really want to draw attention to. Number one, we do have a formula, so we want to make sure we hold that through our whole process. HNMR, so your step one is to ballpark out what they're showing. So 0, I need some help with numbers so I don't have to draw the whole thing. We got a 71533. Oh, is that it? Oh, okay, cool. So we'll max this out at 8. Okay, we'll call this 7, or roughly half a 7 is 3.5. It's never on a spectrum like that, so we'll call that 3. Okay, 2, 1, 5, 6, 4. This is why I teach OChem. I don't have to deal with numbers and scales and all that. All right. So a multiplet is 7.15. What does a multiplet mean?
It has a splitting pattern?
It's just a mess. There's just a bunch of stuff in there. You're not going to be able to interpret the splitting pattern, so don't try. Okay. And a singlet at 3.55. So we drop in at 3.55. We have a nice, theoretically clean and straight singlet. Okay. What other information they give us? Okay. We have a 5-to-2 ratio. What is that 5-to-2 ratio in reference to? The area under the curve, nice dodge. I mean, that's the definition of it. It's known as the... How do you get an area under the curve? Come on, math people. It's an integration. Okay. So what they're effectively giving you, if we look at this question, is they've given us some information about chemical shifts. They've screwed us over on the splitting pattern. We use multiplicity, right? Is the word we use? Yeah. Okay, they give us a multiplicity for the singlet. They said 1 peak. Okay, and if we have 1 peak, what does that mean?
1 signal.
Technically 1 signal, yeah. Let's do a little better than that. How many neighbors? None. Okay, so 0 neighbors. Okay, and then we've got an integration of 5-to-2. Okay, So there are 5 hydrogens represented in this mess called 7, and there's 2 hydrogens represented in this mess called 3. Okay? So if we had something at 7, what does that suggest to us? So now we have to know our chemical shifts. And if that's something that you quickly memorized for the test and decided to ignore, that's okay. You should probably memorize for the test again and then quickly ignore it after the test. Okay? For the sake of homework, don't memorize it, pull it out and look at it. Aromatic. So we're talking about aromatic. We're looking at a benzene ring, which we should get excited about, because if we look at a benzene ring, that gives us a whole crap ton of carbons, okay, with potentially a whole bunch of hydrogens. Could all of those be hydrogens?
No.
Why not?
Well, a few things. There is 6 hydrogens there. When, yeah. And those would all have the same signal, and since we're getting two.
Okay, I accept that. Symmetry in the molecule would suggest those would all come in with the exact same signal, and we'd get a singlet peak. We wouldn't get a multiplet. There'd be no splitting patterns. Okay? I would take it a step further. If those were all hydrogens, can I connect it to anything else?
No.
Which means it doesn't work because I have multiple signals. Okay? So minimally one of those has to be removed. I would take that a step further, and I would argue
Only one.
probably only one. Why only one?
Because there's the integration is 5 to 2.
The integration says 5. Okay? And if I have a 5 there, that means I need 5 aromatic hydrogens. That looks like I just have one missing space. Okay? Depending on how you want to format it, you could format it this way. The way I preference, or what I would prefer to do, would be just show it like this. I would leave the hydrogens as implied and just show the hanging bond knowing it's got to go to something. It's not carbon, it's going to something at this point. Okay? What do I have at 3? Chemical shift-wise. Yeah, I got a giant mess. There could be all sorts of things happening out there. That's going to be kind of hard for me to nuance. Okay, what other information do I have about that signal?
There's 2.
Okay, there should be 2 hydrogens connected to it. Okay, so if I'm just processing through that potential signal, I guess we could color code it, call it that our purple signal. If that's my purple signal, I've got a question mark, but I know there's 2 hydrogens connected to it. Could my question mark be an oxygen?
Yeah. I mean, no.
No, because oxygen should really only have 2 bonds. Okay, so it shouldn't be an oxygen. Could it be a nitrogen?
No.
No, this is not in the chemical formula.
Okay, so, and this was an interesting question just to kind of test. Could it be a nitrogen? Well, yeah, theoretically, because it could have another bond. But if I hold that formula in the back of my head always, I know I don't have a nitrogen in my compound, which means that atom must be a carbon, which means I have 2 bonds hanging off on it. That's all my HNMR really tells me. I could try and play back to the formula. The formula says C15H14O. Okay, how many carbons have I identified so far? 7, not 8. Remember, this is a hanger. I don't know what's out there. So I've got 6 from my ring, and then I have 7. I need 15. That's going to be a little bit weird. Like if I doubled everything, I'd be at 14, not 15.
Well, maybe there's symmetry.
Okay? Well, that's what I was saying. If there's symmetry, I could double everything. Okay? That's going to get me 14 carbons, not 15 carbons. Okay? So there undoubtedly is symmetry. There has to be pretty much. Okay? Because I have to also get 14 hydrogens. How many hydrogens do I have accounted for? I have 7. And if I multiply 7 by 2, yeah, Caden just did the math. That would hit my 14. So more than likely, I have 2 of these, and I have 2 of these.
Yep. And there would be a carbon between.
And there has to be some kind of symmetry allowing those to align. Okay, we can try, oh, I just have a carbon in between. What happens with the oxygen? I'm still missing that oxygen. Okay, so we could go through and say, I've got a carbon chilling out here with 4 potential bonds. I don't know what else too. Okay, and I have an oxygen. I don't like drawing lone pairs for spectroscopy. Okay, and there's an interesting point. Okay, these are not saying they're sigma bonds. I'm just saying I have to have that many bonds for each of those atoms. Okay, it could mean I have multiple bonds. I could have double bonds. Okay, the HNMR doesn't give me any information to say anything about that, but that's where I could then continue on and say the IR spectrum has no absorption in the 32 to 4,000 range, which is telling me what?
There's no OH.
Okay, this tells me that I have no OH. Did I already know that?
Yeah.
Yeah. The HNMR analysis told me that I've already accounted for my hydrogens. I can't drop a hydrogen on the oxygen anyway. So I've got internal confirmation. That's good. Okay. And I've got strong peaks found at 1700. That's a carbon-oxygen double bond, which means this structure that I started to draw down here can now be modified to be a carbon-oxygen double bond. My oxygen's now satisfied, and now the carbon's just missing two
I
bonds.
think it's arguable you could probably solve this without the IR.
Yes, which does kind of introduce kind of another potential situation within most questions that are like this, is you don't need all of the information. What they're trying to provide is a whole bunch of information so that if you have weaknesses in one spot, you can backfill with weak strengths in the other. Okay? So if we go through and take a look at and then they're just giving you the giant middle finger. That's lovely. Okay? So what we're putting together now is we've got two of these rings, we've got two CH2s, and we have this carbonyl structure. Okay? When we talked about this also, these two meant we had symmetry. So it had to double. Okay? Could we potentially use this information to assemble right away?
Yeah.
Yeah. Okay? Could the benzene ring be connected to another benzene ring?
No.
No, why not?
Symmetry.
No, that would be lovely symmetry, so don't tell me symmetry is why it's wrong.
Then it wouldn't connect to anything else?
It can't connect to anything else. There's only one hanger on there. If I attach those two to each other, I can't put them to anything else. Could I attach the benzene ring to the carbonyl?
I mean, you could, but that's probably wrong.
Why? We're just going to call it phenyl.
Get symmetry with the CH2?
We have to maintain that symmetry, and if I'm going to attach that phenyl there, what does that mean the other phenyl has to be? Immediately connected out the other side. And if I do that, can't do this. So the phenols can't be connected to each other, and they can't be connected to the carbonyl, which means the phenols must be connected to a CH2. Okay, which also means the other phenyl is connected to a CH2. And it has to be a new one, because there's two of them, right? That has to be identical. Okay, those are still missing bonds.
That's the carbonyl carbon.
Which is why it wouldn't show up in the HNMR.
And then that carbon, since it has no hydrogens, shouldn't show up in the HNMR, which helps internally explain that as well. We don't see an aldehyde hydrogen. Okay, and what does that mean? We now have the structure of A.
And then the hard part.
Okay, and now we could potentially push into the hard part. Now that we know what compound A is, it makes it a little bit easier because we're not looking at it as just a bubble now, where there's everything being a big mess. Okay, now we're saying what happens when we react. Well, sodium borohydride. Okay, can I erase my spectroscopy work?
Sure.
I got a thumbs up already, so tough.
Oh, so it just adds two hydrogen?
And I add sodium borohydride. Why did I drop off the sodium?
Because they associate.
It's a metal, so I'm looking at borohydride, BH4 minus. How does BH4 minus react?
It literally says it in the question.
No, it doesn't. It says followed by acidification.
Oh.
How does borohydride react?
As in,
Say again?
Electrophile?
To be an electrophile, it would be an electron loving, so an electron acceptor. If it's negative, that doesn't make sense. Nucleophile, what's nucleophilic?
It would have to be the hydrogen.
Good job. It can't be the boron. No, we're not showing a lone pair on that boron. If we added a lone pair to that boron, it would exceed its octet. The boron is only negative because it has too many bonds, effectively. So when we look at sodium borohydride, those electrons are owned not by the boron, but by the hydrogen. Sodium borohydride supplies H-, which means what do we need to find in our structure? Do we have a positive? Yeah, we've got the carbonyl carbon.
On each side of the damn pipe.
Our positive, negative. That first step of that reaction, now I'm getting super simple with that, would give me my oxygen with my negative charge now. Officially, we do have that hydrogen there. I could imply it. And then it says followed by acidification. Acidification means
It will add a hydrogen.
I want a little bit more than adding a hydrogen. Just like up here, I didn't like hydrogen necessarily as a nucleophile. This was hydride, so H-.
Well, this other
Here,
one would be the proton.
it's more appropriate, yeah, as proton. I'd accept proton. Hydrogen hits in that weird gray
Or
area.
where it can technically be either.
Yeah. So it's just a little vague. So it would be H+. That's going to pair up with our negative, which then means our structure B is, ta-da. Whoops, I had phenols. Right, those were phenols.
The importance of remembering what's on your structure.
Yeah. Right. So, and the molecular formula of that product was C15H16O. If we looked at our core fundamental, we were C15H14. All we changed was adding 2 hydrogens. Is that what we did? Yeah. So cool. That fits with the formula as well. Reaction A with CH3MgBr and H3O plus gives us molecule C, which means I now need to move to a molecule C. This was molecule B. C, unfortunately, we're going to go backwards a little bit and probably up because I just don't have a lot of space. Oh, and I erased the stuff that I needed. Good job. CH3MgBr, followed by acidification, or within H+, something like that. Okay.
Isn't that a Grignard?
Okay. Isn't that a Grignard? I'm perfectly acceptable with Grignard as long as you can tell me the next step.
It would take the hydrogen off the oxygen?
No.
What? That is literally the one thing you said it fucking does.
Is there a hydrogen on the oxygen?
Oh, son of a bitch, you're right. There. Never mind.
Okay.
That doesn't make it a file.
So our Grignard, because it's saying the reaction of A, that's this molecule. There's no hydrogen there. Okay. So Grignard, I'm okay with you saying Grignard as long as the next thing out of your mouth is nucleophilic carbon. Okay. You could just go negative carbon. I'm fine with that too. I would argue that's probably better. So negative carbon, which means what do I need to find?
A positive?
A positive. Do I have a positive? Put them together.
Wouldn't, with how you've drawn it, wouldn't the phenols cause some kind of steric, the phenols would cause some kind of steric hindrance with the way you've drawn it?
That's a good question. Give me just a second. And then we get our CH3. That one we can't imply. We'd actually have to show that one. Okay. And then followed by acidification. What does the acidification do?
Make an alcohol? Yeah, that's alcohol. There's no double bond.
Adds the hydrogen onto our alcohol. And now what we have is structure C. If I get real careful with my erasing here, I believe this is the formula for structure C, C16H18O. If we go through and look at the formula change, we added a carbon and we added 4 hydrogens. We added a carbon with 3 hydrogens. Oh, crap. Oh, but there's also the 4th on that guy. So cool. That aligns with the formula as well, which would suggest that we now have all of our answers, and hooray, because we're pretty close to the end of class. So I'll just selectively choose to ignore Anthony's question and we can end class. Steric hindrance isn't a bad topic to bring up, but no, steric hindrance is actually something that we rarely worry about at all within our carbonyl additions. Okay. We do have to worry about it within our enolates. Okay. We're going to get kinetic and thermodynamic. If you didn't encounter that yet, you will. Okay. So we'll talk about enolate kinetic and thermodynamic stuff, and sterics actually technically doesn't even play a role there. Okay? Why is sterics not playing a role with our carbonyls? What's reacting?
Well, the carbon is getting backside attacked.
It's not a backside attack.
It's not?
What's our nucleophile reacting with on the carbonyl?
Positive charge?
Sort of.
The lack of
Slow your roll on the positive charge, but you're in the right vein. What's it reacting with?
Pi orbital?
Give me a little more.
P orbital?
It's the p orbitals. Where are the p orbitals?
Above and below.
Above and below. The rest of this carbon structure
Is
out to the side. I'm reacting up above or I'm reacting down below. Those carbon structures really aren't having any steric effect on the overall reaction because it's the pi system that's reacting. Okay? What this will potentially introduce, if we wanted to get real nitpicky and nasty with it, let's make a subtle change to structure A. Actually, I'm going to make that a CH3. Make that a CH2. If I went through and now had the CH3 react with this,
Oh, you have a chirality.
I would produce a product that has a chiral center. And if I have a chiral center, I'd have to predict whether it was R or S. Is there a preference of the CH3 attacking above or below? No, which means I get both. So when we talk about our carbonyl additions, almost universally, if chirality comes in as a final product, we get two products. Right? You're reacting pi bonds. Pi bonds are going to give you the potential for two products.
Isn't that with almost everything that has a chiral center, it's going to have multiple products?
Well, it can. Think about SN2. Does SN2 give you multiple products?
Yeah.
Okay. It all depends on how that mechanism works and how it functions. When we talk about our carbonyl additions, they are very unselective. Okay. Selective may be the wrong word. There's a sequence of a couple different words that you're supposed to use, and I don't know the English language well enough. But we're going to stick with selective, that it's not choosing one's top or bottom, okay? Which is potentially a problem with carbonyl additions, okay? Which would now be an active area of research. If I want to go through and run a reaction where I do a carbonyl addition and I only want, say, the R enantiomer, okay, what reagent do I use? Well, I don't have one unless I create a reagent that selectively forces one product versus the other.
Well, could we look at a solvent to do something like that?
Solvents usually are achiral, and if they're achiral, they can't have that chirality effect. So what you end up doing is nuancing different ways to pull it off. One way, okay, and I'm going to leave it running. Okay, one way is you could throw in a chiral solvent. Okay, and sometimes just having that chiral solvent present allows a chiral preference of your products. Okay, not always, but sometimes. Okay, other options are choosing reagents that aren't structured so simply. Right? Maybe when you generate this particular structure, whatever that halogen is, you have some other piece that's somehow connected out there that coordinates to the magnesium, okay, still, but has a chirality aspect behind it that selectively preferences one side versus the other. Right? It can be hard to go through a nuance, but because it's hard and challenging, what does that typically mean about people that discover those kind of reagents? It's named after them. Right? So there are different catalysts that are out there that will target certain chemistries and force that stereochemistry. We don't talk about those as much because to me that's on the cutting edge. I would like you to get the basics and fundamentals. I don't need you to know flipping cutting edge stuff.